Find the most acidic proton in the following molecule. You have 5 seconds. Go! You got it? Well, if you decided that the most acidic proton in this molecule is this one, congratulations, you got it wrong. If you decided it was that guy, congratulations again, because you got it wrong again. Now, actually, the most acidic proton in this molecule is right over here. It's this guy. And if you're looking at me right now thinking, what? Then let's talk about that. Hello everyone, my name is Victor, and in this video we're going to talk about how to find the most acidic proton in your molecule. This is by far one of the most common questions in the acid-base chapter in your textbook and in your exams as well, so that's definitely something that you are going to expect on the next exam and on the final, on any kind of standardized exam like ACS or MCAT, etc. So you definitely need to know how to do that. So first of all, when it comes to acidic protons, in order to figure out which proton is more acidic in your molecule, what you want to do, you want to outline the protons that you think are the most acidic, pull them off your molecule and make the corresponding conjugate bases and analyze those. So let's call those protons as proton A, proton B, and proton C. If I were to take my proton A and pull that one off, I would get this species over here. That's going to be my conjugate base. The main features of this conjugate base are going to be the charge that is located on the oxygen, and also I'm seeing that my charge is localized, which means that there is no resonance stabilization here, which is generally speaking not necessarily the best factor to see. We always want to see the resonance stabilization for something with a negative charge in order to make it more stable, or with any charge for that matter. Now, if I look at the proton B and I pull that one off, then in that case I'm going to get a conjugate base that looks like this. Well, this one is actually even worse than A, because now I don't have any resonance, and on top of that, my negative charge is located on carbon, which is not a particularly electronegative element, which means that it will not be able to stabilize my negative charge very well. Finally, if I pull off the proton C, then I'm going to get a conjugate base that looks like this. And the important feature of this conjugate base is that it does have resonance contributors stabilizing our negative charge. We can draw one resonance contributor looking like this, and I can also draw another resonance contributor that's going to look like that. And what jumps at me right away is that these two resonance contributors that I just drew, those ones, they are going to be the major contributors, and on top of that, the negative charge on those is going to be sitting on the oxygen atom. So because of those two major contributors, my negative charge is very well stabilized, and that means that the conjugate base C is the most stable out of all of them, which by extension means that our most acidic proton is going to be proton C, that is sitting in between our carbonyls like that. So you can always use this general principle to figure out whether the certain protons in the molecule going to be more acidic or less acidic by taking the proton off the molecule, making the corresponding conjugate base, and using the 5 factors that we've discussed before to analyze the stability of that conjugate base. And I will quickly remind you that those factors are resonance, atomic size, electronegativity of atoms with a negative charge, inductive effects, and hybridization. The important thing here to remember, though, that factors are more of a general guideline. It's good to know your factors, but it's much more important to know your functional group and the pKa values for those functional groups, and know the generic acidity of different functional groups, what is more acidic and what is less acidic. Generally speaking, the 5 factors that we know that determine the stability of our charged species, they're more like guidelines, they're not set in stone rules, and there are plenty of examples where they can be, well, broken for the lack of a better word. So identifying the functional groups and knowing the acidity of your functional groups is usually a better choice to go here. And And I know that you hate hearing something like that, but it is a good idea to memorize the typical pKa values for different functional groups. I am not talking about memorizing the entire pKa table that you have in front of you, or that your instructor might have given you, or what you have in your textbook, but memorizing the typical pKa values for the most common functional groups will not only save you time, but will also make solving a lot of different acid-base related questions much easier. So among the most typical ones, among the most common ones that you're going to see, the probably most acidic is going to be the carboxylic acid. Those ones, they typically range between 4 and 5, and there are not that many organic molecules which are going to be more acidic than that. Then, when it comes to neutral compounds, the next one is going to be a carbonyl, but not just a regular carbonyl. We're going to be looking for protons that are sandwiched in between two carbonyls like that. So I'm specifically talking about those two protons that I'm highlighting here in red. Those guys typically range between 9 and 13, depending on the nature of the R group. Then we have alcohols. Alcohols typically going to see the acidity at around 16 to 18 pKa value scale. And when it comes to alcohols, they become significantly more acidic if you have any kind of way to stabilize the negative charge on the oxygen via the resonance or via electron withdrawing groups. Of course, it's going to slightly modify that functional group, and instead of an alcohol, you're going to be looking at, let's say, something like phenol. So in the case of phenol, where I have my OH attached to an aromatic ring, well, that one actually has a pKa value at around 9.9. Then, another important functional group that is probably good to remember is going to be a thiol. Typically, thiols are around 11 on the pKa scale. Then, there are a few other numbers that you should probably know, and those are the numbers for your terminal alkyne, which is going to be somewhere around 25. We also have alkenes, so if I have a hydrogen on an sp2 hybridized atom like that, those guys are somewhere around 45. And of course we have just regular alkanes, which don't have any other functional groups. Those are estimated to be somewhere around 55 to 65, depending on the exact structure of the molecule. Couple other things that you are going to see are amines, or NH3+. When they are protonated, they are somewhat acidic, with the pKa ranging from the 9.5 to roughly 10.5, give or take. And when they are neutral, when we have RNH2 or whatever might be the combination of atoms around that nitrogen, for as long as you have a proton on it, those ones are actually around 36 or so. So they are completely non-acidic, and you need short but a miracle to pull the proton of that guy. On top of that, there are a couple of protonated species that might be a good idea to remember. When we have a protonated alcohol or an ether, something of that sort, those species are going to be typically at around -2, so they are fairly acidic. They are pretty much as acidic as it goes when it comes to inorganic acids, because many inorganic acids, they have negative pKa's as well. Then another protonated species that might be useful for us is a protonated carbonyl. So when you have a CO double bond and you have an extra hydrogen sitting on that like that, those are actually even more acidic and sit somewhere around -7 to -6, give or take. And finally, two more species that you are going to see within the scope of your course quite regularly, or I should actually say 3 species. 2 of them are protonated. One is going to be the pyridinium ion, which looks like that. This number is going to be at 5.2. We are also going to relatively frequently see the aniline, and I'm talking about the protonated version of aniline, which is around 4.6. And of course we have water, which has a pKa of either 14 or you can see the value of 15.7 in some textbooks. There is a hot debate whether it should be 14 or 15.6. The thermodynamic data suggests that the pKa of water should be 14. However, 15.7, it's a historic value that has been proposed by Bronsted himself, and it has been in the literature for a very long time by now. So if your instructor insists upon using 15.7 and if that is something that you have in your textbook, well, that's what you're going to be using within the scope of your course, despite the fact that 14 is probably a more correct one based on the thermodynamic data that we have. So these are the numbers that you probably should commit to memory in order to make your life in organic chemistry much easier. I understand that it's a lot of numbers, so I'm not saying just sit down and just, rote memorize those things. Make a list, make a cheat sheet for yourself, make a few copies of that, stick it around your house, put it under the binder cover of your organic chemistry binder, someplace where you can look at it from time to time, maybe look at it once a day, and you will be surprised how quickly you will memorize those numbers, because I can guarantee that these are the numbers that you are going to be using in your course all the time. So knowing your functional groups and knowing the typical pKa's for those functional groups will be your saving boat more than once on the exams and homework, and it will also save you a ton of time. I can guarantee you that. So let's see how I can use these factors on a few examples. The first example that I have here for you is a molecule that looks like this. I have an alcohol functional group and I have a carboxylic acid functional group. From my knowledge of functional groups, I know that the carboxylic acid that I have over here, this is my carboxylic acid, that is a significantly more acidic functional group than an alcohol. Carboxylic acid, a typical value, the pKa value for a carboxylic acid is going to be somewhere between 4 and 5, 4 and 6, while the alcohol that I have up there, that one is going to be somewhere between 16 and 18. So right away, by identifying my functional groups, I know that the carboxylic acid is going to be significantly more acidic, and by extension, the proton on the OH of the carboxylic acid is going to be my most acidic proton. Now, often, when it comes to the homework or when it comes to the exam questions, you will be asked to provide your reasoning. And of course, you cannot say that my reasoning that I know that carboxylic acid is more acidic or I know the pKa value, that's ain't gonna cut it. So when it comes to the reasoning here, now we are going to use the factors to explain why carboxylic acid is more acidic than an alcohol. If I were to draw a conjugate base that I would make by deprotonating my carboxylic acid functional group, I would get something like this. This functional group does exhibit a resonance, which means that my negative charge is going to be stabilized by the resonance. It's going to be delocalized. So I do have resonance stabilization there. And if I were to draw a conjugate base that I would get by deprotonating my alcohol, I would get something like this. No resonance stabilization, no delocalization of my negative charge, or any other good effects that we know that would stabilize my negative charge, which means that my conjugate base for the carboxylic acid is more stable. And because of that, that gives me a more acidic proton. And I will also know that it's more stable because of the resonance. Okay, next example, I have a molecule that looks like that. I have an aromatic ring, I have an OH group on that, and I have another OH group. So on the surface, it looks like I have two alcohols here. However, if I pay very close attention, I can see that my pink alcohol over there on top is connected directly to the aromatic ring. So I know that whenever an alcohol is connected to an aromatic ring like that, that actually makes a phenol functional group. While the blue OH that I have on the right side is not connected to anything of any significance. It is just connected to an sp3 hybridized carbon, and that carbon doesn't really do anything. So I know that phenols are more acidic than regular alcohols, so I know right away that my OH up top, the pink OH, is going to have the most acidic proton. Now, how would I explain that with my factors? I'm going to, like in the previous case, draw the conjugate bases for both and see what's going to be the difference. So in the first case, I'm going to end up with a conjugate base that looks like that with a minus on my upper oxygen. That minus is very well stabilized via the resonance, so I can draw a ton of resonance structures here, and I'm not going to draw them at the moment. However, I do challenge you to grab a piece of paper and draw all the resonance structures there. You should end up with additional 3 resonance structures. So I'll put in parentheses that we have 3 resonance structures here, and all of them are going to be minor structures over here, because in all of those cases the negative charge is going to end up on the carbon instead of oxygen, and we're also going to disrupt the aromatic ring, which is going to decrease the overall stability of the hybrid. Now, if I do the same trick for the blue proton, then in that case my conjugate base is going to look like that. I'm going to keep my phenolic OH just as is, but for the blue one, I now have a negative charge on this oxygen. Now, this oxygen is localized. I do not have any kind of resonance stabilization for my negative charge, which means that, well, that negative charge cannot go anywhere. The only good thing that it has is the fact that it's on the oxygen. But other than that, it's not necessarily a super stable negative charge, so we don't have anything going for it, which means that the conjugate base that I drew for my pink proton, which is going to be on that oxygen, is more stable, and by extension that explains why the pink OH group is more acidic. Now here is another fun example. In this example I have a triple bond connected to a chain which contains an NH2 group. Now, up to this point, I've typically targeted my heteroatoms like oxygen, nitrogen, etc. as the potential place for the acidic proton. In this case, I can do the same thing, and if I didn't know the pKa values, I might have said that the protons on the nitrogen are going to be more acidic. But I do know the pKa values for different functional groups, and I know that for amine that is 36, while the terminal alkyne has a pKa value of about 25. We have over 10 to the 10th power difference between those, which means that the terminal alkyne in this case is actually going to be significantly more acidic. This is the example where our general rules kind of break, because if we think about the laundry list of the rules that we have, we've got resonance, not applicable for either of those. We have the atomic size, not applicable because carbon and nitrogen are in the same period, so size-wise they are the same. We have then electronegativity. Nitrogen has a higher electronegativity, and yet carbon in this case will be able to stabilize negative charge much better because of the triple bond and sp hybridization. So all of a sudden, one of the minor factors that we almost never look at, hybridization, becomes something very important for us. And unless you knew the exact pKa values for these functional groups, you would have never guessed that. You would have gotten this question wrong, and you would have said that NH2 is more acidic, while in reality it is the terminal alkyne and this hydrogen that is the most acidic for this particular molecule. Now here is another example. In this case, again, I'm going to first of all look at the protons that are attached to my heteroatoms. I have an alcohol with an OH, and I have a thiol with the SH. I know from the pKa perspective that thiols have a pKa value of around 11, while alcohols have a pKa of roughly 16 or so. So I immediately know that thiol is going to be more acidic. Anything else that I have around in my molecule, if let's say I look at the proton over here, well, that one is a proton in a regular alkane, so we can expect somewhere around 50. If I look at the proton over here, that one is going to be on the sp2 hybridized carbon, so we can expect that one to be like 45 or so. Everything is significantly less acidic than either alcohol or thiol. And of course, if I needed to employ my factors for why thiol is more acidic than OH, I can always argue that when I have O- versus when I have S minus for my conjugate base, sulfur is a much larger atom, which means that it's going to stabilize the negative charge much better than a smaller oxygen atom. In the next example, I don't have any hydrogen sitting on the heteroatoms like oxygen or nitrogen or sulfur, so I might be tempted to look at the hydrogen connected to my CH3 group simply because that one is kind of spelled out or highlighted. However, that is a common trap. It's a common trick that a lot of instructors are going to use because in this case, the hydrogen is attached to carbon, but we have more places in our molecule where the hydrogen is going to be attached to a carbon. We have a hydrogen atom attached to a carbon in the middle of the molecule, and we have a hydrogen atom attached to our molecule at the very edge of it. So I have three cases. I have case, let's call it A, case B, and case C. So if I were to take all of those possible conjugate bases that I will form in each of those cases upon pulling the proton off and make my conjugate base and analyze those, then what I'm going to have for A is the molecule that's going to look like this, where I have my oxygen next to a carbon. It's now going to be a CH2 group with a negative charge on that. In the case of B, I'm going to end up with a negative charge in between two carbonyls right over here, and of course I'm going to draw the rest of my molecule. And in the case of the molecule C, or in the case of the version C, I should probably say, I'm going to end up with the negative charge on the edge of my molecule next to a carbonyl like that. I know, based on my knowledge of the pKa values, that proton B has a pKa somewhere between 9 and 13, which means that that one is probably the most acidic proton in this molecule because this is something that I have highlighted previously. But let's say I didn't know that, and in this case I'm going to use my factors. Well, in the case of A, I can see that there is absolutely no resonance stabilization if I try to push my electrons towards the oxygen, while oxygen already has a full octet around it, so we cannot do this type of resonance stabilization, which means, well, there is no resonance there. And on top of that, my negative charge is sitting on the carbon atom, which, as we know, cannot really stabilize the charge very well. In the case of B, I can do resonance either to the right or I can do resonance to the left. In this case, I'm going to end up with two resonance contributors. The first one is going to be with a negative charge on the oxygen, just like that, and I have the rest of my molecule, while in the other case, I'm going to have a negative charge also on the oxygen, but now that oxygen is on the right side, like so. So now, like in one of the cases that I've had before, I do have two resonance contributors, and those are two major resonance contributors, which is a good indication for the stabilization of the negative charge. And on top of that, oxygen in those contributors is bearing my negative charge, so that is also an extra stabilization factor. And of course, I do have some resonance in the case of C, but in the case of C, I will only have one other meaningful resonance structure that will be able to stabilize my negative charge, and that resonance structure, while it is in fact a major contributor as well, there is only one resonance structure that I can draw here in addition to my original one, and only one major contributor that I have in the case of the molecule C is significantly less effective in stabilizing the negative charge than the two major contributors that I have in the case of the B. So using our factors, we can easily see that in this case, our proton B is going to be the most acidic for this particular molecule. And of course, your factors become exceptionally important when we are dealing with the acidity connected to the same style of a functional group. So what I mean is, let's say I have a molecule like so, where I have one alcohol on one side of the molecule and I have another alcohol on the other side of the molecule. Well, in this case, the most acidic proton is either going to be my proton A or it is going to be my proton B. And in order to find out which one is my most acidic proton, I would have to do my analysis and see which kind of factors I have that will be able to stabilize my negative charge on both of those once I pull my proton off. So in the case of A, if I were to pull that proton off, I'm going to have an oxygen with a negative charge, then I will have the rest of my molecule like so. In the case of B, the left side of my molecule is going to be unchanged, so I will quickly redraw that. However, the right side now will have an O- instead of OH. Looking carefully at the negative charge and where it is located, I see that I do not have resonance for either of those, because if you thought that I can do resonance over here, well, the atom that I have next to my oxygen on the left, that is an sp3 hybridized atom, which means that there is no way I can do resonance there. We already have full octet around that atom, and it physically cannot accept any more electrons, so no resonance in either case. The negative charge is located on the oxygen in both cases, which does mean that we have no difference from the perspective of the electronegativity or atomic size, because oxygen there, oxygen here, no difference. Finally, we are going to look at the inductive effects, and that is where we have difference. On the left, we have a CO double bond relatively close to my O-, while on the right side, my CO double bond is significantly further away. And as I've mentioned in my previous video, when it comes to our inductive effects, they easily die out within 3 to 5 bonds. So the one on the left is located essentially 2 carbons away from the place where my negative charge is. If I look at the one on the right, then I have 1, 2, 3, 4. So now we have 4 carbons away. We are twice as far as what we have on the left side, which means that the inductive effect on the right is significantly weaker than the equal inductive effect that we have on the left side. So, by extension, we can say that our conjugate base on the left is more stable, which means that the proton A is the most acidic in this molecule. And before I wrap up for this video for today, I want to unravel or break one of the very common misconceptions that I hear all the time. And the misconception is that a positively charged functional group is always going to be more acidic than a neutral one. That is a case in many cases, but it's not a general rule. Overall, when it comes to organic chemistry and chemistry in general, whenever you hear some sort of a blanket statement that, everything that's positively charged is always more acidic, you should be extremely cautious about that. Blanket statements like that are exceptionally rarely true. Most of the time, that is going to be a gross oversimplifications, and most of the time it's just simply not going to be true. So here is an example of, let's say, glycine, a common amino acid. When it is in the fully protonated form, it looks like that. If I were to look up the pKa values for both of my functional groups, I have the carboxylic acid on the right side, while typical carboxylic acid's pKa value is going to be somewhere between 4 and 5. This one happens to be at 2.4 because of the presence of the nitrogen next to it. The nitrogen on the other side, the protonated amino group, the typical pKa for those is somewhere around 9.5 to 10.5, and for this particular one it happens to be at 9.8. So we can clearly see that the carboxylic acid is not just a little bit but significantly more acidic than our protonated amine, which means that in this case, as you can clearly see, the neutral functional group is more acidic, and more acidic by far. We're talking about good 7 orders of magnitude, so it's by far more acidic than a protonated one. So don't make a hasty assumption that if you see a positive charge somewhere, it automatically going to make your functional group more acidic. That simply is not true. So always remember your functional groups before you just blindly follow the factors or some sort of easy tricks. So as a quick recap, I want to remind you to prioritize the functional group knowledge, Look for the difference in the functional groups and the factors when you have the same functional group. And of course, to make your life easier, memorize those common functional group pKa values that I have told you about at the beginning of this video. Let me know the feedback or questions that you might have in the comments below, and I will see you in the next video.